Hi, my name is Christian Serio, and I'm currently a fourth year PhD student in the mathematics department at Stanford University, advised by Amir Dembo. My research focuses on a mathematically rigorous approach to statistical mechanics through probability theory. Broadly, the goal is to understand how, in a complex physical system, random interactions of the many microscopic components coalesce to create order on the macroscopic scale. A particular class of models that I'm interested in are random interfaces. These models generally describe the separation of different phases in a physical system. Some concrete examples include the shape of a droplet of liquid condensing onto a solid, the front of a spreading wildfire, or a growing bacteria colony. There's a striking phenomenon in statistical physics known as universality, in which models that seem microscopically very different from one another appear similar on the large scale with common universal scaling limits. Many interface models are expected to lie in the so-called Kardar-Parisi-Jean, or KPZ, universality class, first proposed by three physicists in 1986. It's a major open problem in mathematics to give a rigorous and complete description of this KPZ universality class, and one of the primary goals of my research is to develop techniques and results establishing universal KPZ limiting behavior for random interface models. One method that I've used to study these random interface models, particularly in two dimensions, is to look at the contour lines of the surface. You can imagine drawing a topographic map with one-dimensional curves indicating locations where the surface is at a given height. In this context, the KPZ conjecture is that these random curves should have fluctuations described by certain special probability distributions, known as Airy processes and the Tracy-Widom distribution. An advantage of viewing a surface in terms of these contour lines is that the curves display certain Gibbs properties. Locally, they look like familiar objects from probability theory, such as random walks or Brownian motions. Much of my past work has developed tools to analyze ensembles of such random interacting curves. This has allowed my collaborators and I to prove results describing the universal large-scale behavior of various random interface models, including, for instance, the 2+1 dimensional solid-on-solid, or SOS model, which was introduced by physicists in the 50s to describe a growing crystal surface and also has applications to the theory of ferromagnetism. To close, the support of the ARCS Foundation has been extremely helpful in allowing me to pursue this line of research, and I look forward to continuing to do so. Thank you very much.